Good afternoon, everyone. I'm Mukesh Krishna, your host for today. It's a pleasure to welcome you all to this special session hosted by ACM VIT and Score School. Before we begin, let me introduce ACM, the Association for Computing Machinery. ACM is the world's largest and most significant computing society, dedicated to advancing computing as both a science and a profession. With over 100,000 members worldwide, ACM brings together educators, researchers, and professionals to foster collaboration, share knowledge, and address some of the most pressing challenges in technology. It is committed to maintaining the highest standards of the computing profession, supporting lifelong learning, career development, and professional networking. For students worldwide, ACM has established student chapters in over 500 colleges and universities, creating platforms for collaboration, networking, and learning. The School of Computer Science, Engineering and Information Systems, the SCORE School, emphasizes on fields of information technology, software engineering, digital communication, multimedia, and computer application. The prime focus is to promote the effective integration of technology with state-of-the-art facilities in teaching and research activities. The curriculum of various programs offered by the school focuses on problem solving, design development, and application of various emerging technologies. Now, let me tell you about ACM VIT. ACM VIT is proud to be a part of this influential organization. Since our founding in 2009, ACM has been dedicated to advancing computer science as a meaningful and impactful profession. We see ourselves not just as an organization, but as a family, united by our motto, because technology matters. This principle guides our work, driving us to make technology more accessible and impactful. Our chapter is involved in diverse projects and initiatives across fields like graphic design, web development, machine learning, and app development. We organize regular workshops and events that foster hands-on learning and skill development. We are also proud to have our own research wing, which explores forward-thinking initiative over the years. ACM VIT has earned a reputation for quality, creativity, and innovation, producing exceptional projects such as Exam Cooker, which is a one-stop place for all your exam needs, and Unipool, which is a carpooling app, and CLI RPG, which is a CLI game made with Rust, and ACM One is a hub for all of the students of ACM VIT. Now, alongside ACM VIT, we are also proud to be a part of ACM W, ACM Women. It is a dedicated branch in advancing contributions of women in computing. ACMW India takes forward ACM's mission with a specific focus on empowering women in computing across the country. It supports, celebrates, and advocates for the engagement of women in all aspects of the computing field. Through ACMW, student chapters and professionals chapter sponsored activities, ACMW India provides educational and networking opportunities that inspire women to pursue and thrive in computing careers. This initiative is vital in creating social and professional support networks, and we are honored to contribute to this mission at ACM VIT. At this point, I would like to acknowledge the invaluable support of our faculty coordinator, Dr. Ashwani Kumar Cherukuri. Dr. Cherukuri is a distinguished professor in cybersecurity and cryptography, with over 150 research publications to his name. As a senior member and senior ACM member and the vice chair of IEEE's task force on educational data mining, he brings vast expertise and dedication to our chapter. Recognized among Stanford's top 2% scientists globally, Dr. Cherukuri's guidance has been instrumental in helping ACM VIT thrive. We're grateful to have such an accomplished mentor whose contributions strengthen and inspire our work every day. I'd like for him to say a few words. Okay, sir isn't available, so we shall be moving forward. Now, it's my honor to introduce our speaker for today, Dr. Federica Sarro from University College, London. Dr. Sarro is a distinguished leader in the fields of search-based software engineering, empirical software engineering, and software analytics. Her work in automated software management, optimization, testing, and repair has transformed modern software systems. Today, Dr. Sarro will be presenting on search-based software engineering for modern software systems. Her talk promises to provide fresh perspectives on optimizing software development and performance through data-driven approaches, inspiring us all to explore the future of software in bold new ways. Now, Dr. Sarro's, to conclude, today's session with Dr. Sarro's perfectly aligns with ACM VIT's mission of empowering students to learn, grow, and push boundaries of what's possible in computer science. We are truly grateful for the opportunity to host Dr. Sarro, and I'm confident that her talk will leave us all inspired. Now, please join me in welcoming Dr. Federica Sarro.
Okay. So thanks everyone for joining this talk. I'm Professor Sarro, work at University College London in the United Kingdom, and I'm the head of the Software System Engineering Group at UCL. And today I will present you the work we have been doing on search-based software engineering for modern software systems. As I mentioned, I'm the head of the Software System Engineering Group. This is a large research group that was set up at UCL in 1999. And we have several academics, postdoc, PhD. What is maybe interesting for you is that we used to host researchers at all grades, so from PhD to postdoc to professors. So if you would like to visit us, it's possible to make an application. And within SSE, I've established a group focusing on working on software optimization, learning, and analytics. And on our website, you can find all the research topics we work on, the publication, and some open source artifacts. And we also have recording of our talks on YouTube. Mainly we're all part of the CREST Center, which was established over 15 years ago by Professor Arman. And the research area for the center are capturing this word cloud here. And one of the things we work a lot in CREST is search-based software engineering, but we also contributed to many other topics on specific domains around this main idea here. And today's talk will show how we what is search-based software engineering and how we can use it to address problems in modern software systems like AI-driven systems. And we generally work in collaboration with several companies. Some are summarized here and get funding both from European Union and the UK Research Council. Without further ado, let's dive in the topic of this talk. So programming has been changing in the last 5-6 years because realizing modern software systems, especially, as I said, AI-driven ones, poses new challenges to software engineers. If you have application running on limited capability devices, users want acceptable performance. If you use artificial intelligence to make decisions within your software system, you need to make sure that these decisions are fair to all users. If you are on a social network, you have the expectation that you need to be protected against other malicious users and so on. So, well, the main mission of traditional software has been to provide the user with the right functionalities. Nowadays, as software engineers, we are called to realize software able to tackle a growing demand of non-functional requirements, for example, to reduce energy consumption, improve fairness, increase safety, among others. But are we ready as software engineering to cope with such a demand? Let's see an example. Imagine a group of software engineers being asked to implement a camera functionality for a software. This sounds very doable, right? So we expect everybody to be able to do it. Now let's add it a new requirement as recording and playback functionalities. While 1 or 2 developers might find this difficult, the rest are still managing okay. if we add some printing option to the same software that took a few other developers down, and on top of those non-functional requirements like storage, execution time, memory consumption, energy, connectivity, to name a few. And it's almost impossible for a human to keep up with this growing demand of requirements. Moreover, nowadays, software engineers are required to develop software on multiple fronts. For example, software should be accessible on several operating systems, multiple devices, and should take into account multiple objectives, which are often conflicting with each other. So we cannot expect that the software engineer, regardless of their level of expertise, will be able to manually find all opportunities for optimizing these non-functional properties. And while we all agree that humans are the most suitable to define software functional and non-functional requirements, we cannot expect them to be able to manually code, to manually achieve all of them when realizing a software system. So in this talk, we'll see how a machine can reliably use to automatically optimize both functional and non-functional properties. And in particular, in this keynote, I'll discuss the way in which search-based methods can help developers achieve automated optimization on non-functional properties. For example, ethical challenges posed by AI system, including software fairness and software footprint. So let's understand together what is search-based software engineering. In short, SBSE. SBSE is an approach to software engineering in which search-based optimization are used to identify search-based optimization algorithms are used to identify optimal or near-optimal solutions and to get insights into software engineering problems characterized by a large space of possible solutions. And this large space cannot be exhaustively explored in a reasonable time. So we use, in fact, search-based optimization algorithms or heuristics. SBC has been successfully used for improving several software engineering processes, from software management to software testing and repair, as well as improving tools used by developers and functional and non-functional properties of a software itself. In fact, several of these several software engineering problems are characterized by a large space and multiple competing goals, where it is often not clear how to achieve an optimal solution, but it's more clear how to evaluate and compare different candidate solutions. For instance, it may be hard to know how to achieve a software design, architectural design with low coupling and high cohesion, but it's relatively easy to decide, given two designs, to decide which one is more closely coupled than another design. And in SPC, we exactly aim to write a method to determine which is better of two solutions, instead of writing a method to construct the perfect solution. And this is the main difference between conventional software engineering, where we are asked to provide a solution that solves a problem with certainty, while in search-based software engineering, we are aiming to write a method that is able to determine, given two solutions, which one is better at solving that problem so that we can build approximate optimal solution rather than perfect one. Ideally, you want the perfect one, but as we said, it's generally hard to find one in such large search spaces. So this method that we use to determine which is better between two solutions is usually called fitness or objective function in the literature. And the fitness function is used to effectively guide the search towards an optimal solution from a large number of alternatives. So in summary, SPSC applies search techniques to explore large spaces guided by an objective function that captures the properties of interest of the software artifacts we seek. Here in these slides are summarized a few examples of these search techniques: tabu search, hill climbing, and colonies, genetic algorithms, and give you just an example of how a genetic algorithm work. So genetic algorithms, in short GA, are perhaps the most famous search-based approaches, the most used because they're very powerful. A genetic algorithm performs a global search and is an algorithm inspired by the Darwinian theory of natural evolution. This algorithm starts from a random set of solutions which are called individuals and creates consecutive population of individuals considered as feasible solution for a given problem, to search for a solution which gives the best approximation of the optimum for the problem under investigation. So to this end, we have fitness function that evaluate the goodness of each of these individuals, and some operators which are called genetic operators that are based on selection and reproduction. These operators select individuals from the current population and mix them in a crossover way, or mutate them, introducing some random new random characteristics in the population. And so individuals may reproduce themselves into new solution, and the population may evolve gradually towards a stronger and better quality solution over time. So in order to use a genetic algorithm, you need to have a representation of your solution. Usually this can be done by vectorizing the problem, an objective function which measure the quality of the solution, and this operator that I just described. One of the most recent applications of SPSC is the use of genetic algorithms to automatically modify software source code, and this is called genetic programming. And I'll give you an example of how GA can be used to modify software code for program repair. So we have a piece of software, it has a bug, and we want to create automatically a patch to solve this bug. Okay, so a candidate solution to our problem is called candidate patch, and this is basically a series of statements in the code. So this one in the slides is an example. Is delete statement X, replace statement X with statement Y, and insert statement Y after statement X. So if you do these three operations on the code, you're supposed to fix the code automatically. If the candidate patch is obviously good. How we measure this candidate patch is good? We apply this to the software code, we do this changing, we run the code, and we check how many test cases are passed. We see that the software was previously buggy, so there was at least one test case failing. A good patch will make the software pass all test cases, including the one that was failing before, and won't introduce new fault, so won't break other test cases. So we use the suite to determine the correctness of a patch. And the fitness function in this case can just count the number of test cases passed by a given solution. And to mutate an individual, we can, for example, add new random methods to an empty patch. So in this context, we start from an input file containing the source code of the buggy software component. And you can see here we're passing 4 test cases, but one is failing. And we iteratively create multiple mutated versions. In each mutated version, there is a patch, and each of these is evaluated with the fitness function we just described. So for each of them, we count how many test cases are passed. and continue evolving this according to a genetic algorithms process until an optimal solution is found, or a budget, our resource budget is consumed, basically, which is more often the case. You define a maximum number of iterations of this process, or maximum amount of time, say 3 hours, to run the algorithm, and then at the end, the best solution is retained. So we've just seen how search-based approaches can be applied to improve program functionalities through bug fixing. Now I would like to discuss how these approaches can also be used to optimize non-functional properties like fairness, energy, and energy consumption. In fact, non-functional properties can be optimization objectives as well. So the idea will be to create multiple versions of the software, each achieving a certain optimal trade-off between two or more objectives. So each circle in these slides is a program, a software program that has been found by a machine, by an automated algorithm, similar to the one we explained before. And each of these programs has different values for the objectives we're optimizing. In this example, we want to optimize energy consumption and execution time. Okay, so we have here a set of software programs satisfying this objective in different ways, and representing a solution space. When we change objective, we'll have different solution space, because different non-functional properties have different distribution, basically. And what is important is each of these programs is equally optimal with respect to the trade-off between the two objectives, because these objectives are competitive. We can't, for example, optimize both for execution time. We can achieve a solution that has the minimum execution time and the minimum energy consumption. If you want something to be faster, perhaps you consume more energy, but there's some trade-off that we can achieve among these value. So what is called Pareto forms in the literature is a set of solutions that is equally optimal with respect to the trade-off between the objectives given. So a solution is called Pareto optimal if none of the objective functions can be improved in value without worsening some of the other objectives. And without additional preference information given by the user, there may exist a number of Pareto optimal solutions, all of which are considered equally good. And what's the goal of using multi-objective optimization? Well, we can have three aims. We can find a representative set of Pareto optimal solutions. We can quantify the trade-off and satisfy these different objectives. And we can also find a single solution that satisfies the subjective preferences of the end users. We can also tackle many objectives at times. For example, 3, if we consider memory consumption in addition to execution time and energy. And here we're just considering non-functional properties, but there's one more thing that we can do to further understand the search space. We can focus on opportunities for performance improvement under two different oracles, exact and approximate. An exact text oracle requires the original and improved programs to produce identical output. So we want absolutely that the program behavior remains the same. So we optimize for energy consumption, yet we don't want any fault in the program. Instead, what is called approximate test oracle use a more relaxed notion or whether the output of the improved program and the original program is acceptable, where we can allow for some failed test cases. This may be surprising, but not in all applications is extremely important that you have a perfect functional software. In fact, it has been, for example, a mobile application can trade the aesthetics of the user interface for a better energy consumption, or a graphics-based application can trade image quality. So in this case, the deviation from the precise output of the original program may be tolerable if there is a great decrease in energy consumption. And in a survey of software engineers responsible for systems in which energy consumption is very critical, the majority of them, about 80% of engineers, were willing to sacrifice other requirements in order to obtain a reduced energy consumption. And here is an example of using an approximate oracle. In this IEEE Transaction Software Engineering paper from 2017, Bruce and others studied the search space when optimizing the energy consumption of 4 software systems by using genetic algorithms. And these slides will show the output from 2 versions of a body track software system. The image on the left is generated from the original application, and the image on the right is generated from a modified variant that has been obtained with genetic algorithms. And the body tracking on the right is approximate. You see the face is not identified 100% correctly, but the rest of the body still it is. And it takes it takes about 33% less energy to be computed. So if we can accept that degradation in recognition quality, we can save energy. And approximate text oracles permit trading quality attribute against energy consumption, which, as you see here, has been proved to be effective. Of course, it depends on the application domain. You may have, when you go at the airport and they do facial recognition, you will need to be 100% accurate, no matter what energy it consumes. But if you need to just put an object in motion, this approach could be good enough. And for example, if you use it on an autonomous driving car, saving energy, saving the battery of the car, yet being able to identify other object in motion, despite not completely 100% accuracy, could still be safe. So this subfield of search-based software engineering that uses automated search to find improved version of existing software is called genetic improvement of software. And the overall goal is to mutate software to find improved software versions. So search-based software engineering, and in particular AGI, can help developers to tackle non-functional properties of modern software system. For example, to reduce software carbon footprint, software energy consumption. In fact, the footprint caused by the usage of communication computing technologies has been expanding globally in the last decade, with rapid and ever-evolving adoption of ubiquitous mobile device and AI-enabled system for everyday life activities. And software contributes to energy consumption on par of other attributes as hardware, data, and network. Here is an example of carbon footprint consumed by modern AI models. Let's refer to one of the latest AI breakthrough large language models. As you all may know, example like ChatGPT or AI models able to answer a variety of questions, compose essay, a philosophical conversation even, and in our field they're able to write code, repair code, and so on. However, all these wonderful things come at a very high cost. When I asked ChatGPT how much energy does training such model consume, the reply I got is written in the slides, and in summary, ChatGPT replied that for training the largest GPT-3 model, which is not even the latest model, is the equivalent of a typical American, consumes the equivalent of a typical American household for 291 years. So just training one model, it consumes that much. And we are going to do something about that. I'll show you one approach we have recently proposed to tackle energy consumption of generative AI in the context of text-to-image generation. So in recent years, generative AI, or in short, Gen AI, has emerged as a powerful approach that enables machines to generate different content, such as text, images, and videos. Particularly text-to-image generation have garnered significant attention due to their potential in translating human language into visually meaningful representations. So this facilitates a lot of tasks, such as generating imaging for books, product image for advertising, inspiring artists to create new form of art, but also help us with our presentations, for example. And achieving optimal image quality involves tuning various parameters, such as number of inference steps, positive and negative prompts, and so on. And last year we have used genetic algorithms to optimize image quality of Stable Diffusion. Stable Diffusion is one of the most popular open source tool, Gen AI tool, to produce images. And you can see in these slides an example of the output of our approach. So if we have a prompt asking Stable Diffusion to generate an image with two people and a bus, on the left image, we have the output of Stable Diffusion before parameter tuning. It shows only one person. The bus is clear, but shows only one person, so it's not precise. And in the second picture, picture B, we see the image after parameter tuning applied with GA. You can see there are clearly two people, for example. However, using this type of approaches is more critical role, while simply increasing computational resources do not translate to better image quality. Instead, identify optimal parameters to balance computational efficiency and output quality are much more crucial, basically. So to sum up this part, in text-to-image generation, achieving images of high quality is often not only the only important aspect to consider. Inference time, which directly impacts user experience and energy consumption, also plays a critical role. In this work, we have introduced Green Stevoliolo, an eco-friendly approach using multi-objective genetic algorithms to strike an optimal trade-off between these two objectives for Stable Diffusion. And future research can expand upon our evaluation by incorporating alternative initial prompts, optimize different performance measures, for example, carbon footprints, and trying, for example, other Gen AI system We make the code available. It's an open source tool, so everybody can use it and try it out. So before we move to software training, I'll just take like 30 seconds break to drink some water. If anyone has any question up to this point, I'm happy to take them as well. Otherwise, we'll do it at the end. I don't know if there been any question or text in the chat, because I can only see the slides. The laptop doesn't allow me to switch back to Google Meet. So if you have any questions, just open up your mic and speak, basically. It's fine if you...
Hello?
Hello?
Yeah. Hello, Professor. So you were speaking a lot about many companies or like anyone who has a software solution focusing more on energy usage rather than optimizing the like functional properties of the software. So considering that many AI leaders are now considering moving to nuclear energy and stuff like that to like fulfill their requirements. As far as I know, I think Google recently leased out a nuclear plant to fulfill their energy requirements. So do you think that for the next whatever AI revolution that's going to happen, like energy optimization is the like most the biggest problem that is going to be faced by the industry?
Well, yeah, I mean, the energy problem is twofold. On the one hand, they will need more energy to run even more powerful techniques, because that's their main goal, right? Get revenue, so have very performant techniques. But this has the drawback for the environment. They have all the money in this world to get more energy, but they need to be careful about how they do use this energy, because it has a growing environmental cost. So we need to find a way to incentivize them to invest into better data centers, and this is what they're working on, better network usage, but also optimizing the actual software itself. And in this, as engineer, we can play a role, because we can write better, optimized software for energy consumption. So this is definitely a challenge for companies. When it comes to AI, software is not the only one. I will move into software fairness, and I'll explain a bit more about this problem, which is also important for many companies, especially in light of now of the AI Act in Europe, for example, that impose companies to adhere to strict regulation in the use they do of their AI, both in terms of software, energy consumption, and fairness. I hope they answer your question. In the past years, there's a new type of defect in our software that has been manifesting more and more frequently. This defect relates to the software ability to perform in a fair manner. And as a result, sensitive attributes like gender, age, race, religion have been highlighted as attributes that should be protected from the decision made by our software. A person's race, for example, shouldn't be the reason people are accepted or denied alone when using automatic system to take decision. And while software system may learn bias from biased data, unfairness can also emerge from ambiguous or incomplete requirement specification, poor design, and implementation bugs, making fairness and non-functional properties, among others, highly related issues to software quality, basically. So this has huge growing interest on defining, evaluating, and improving fairness in AI algorithms. And we've just published a survey on this topic, how we can test AI system for fairness. And here on the slide there's a reference, and you can read about papers published on this topic up to 2024, basically. 2023, actually, because we published this year. So what is fairness? What is discrimination? For machine learning software, individual discrimination and group discrimination can be defined as follows. For individual discrimination, given two inputs to a machine learner, where these two inputs only differ in their protected attributes, for example, race, we expect the model to give the same output. If the prediction of the model is different for these two inputs, then we see that the model is discriminating. Similarly, for group discrimination, a machine learning model discriminates or favors systems belonging to a specific over other group. For example, we may have an algorithm that favors males. For example, if two people with an identical qualification, identical professional qualification, but different genders apply for the same job position, their likelihood of getting the position should be in no way affected or influenced by the fact that they're female or male. And we observed in the real world that automated software system using AI approaches to make decisions about job interview selection were biased. There's been a huge case for Amazon a few years ago where they were using an automated approach to do CV screening. So the AI was looking through the CV and decide which people to put forward for interview, and it came out that it was favoring male over women. So male were getting access to interview more often than women. So while in traditional software system, bugs mainly arise from how developers realize the decision logic. In AI-enabled software systems, there are other aspects such as training data, feature sets, algorithm selection and tuning that may incur in bugs, and some of these bugs may be fairness bugs. So in order to fix fairness bugs, we can apply what is called a bias mitigation method, which goal is precisely to reduce bias in classification models. And when these models are applied to remove bias by manipulating the training data, they're called pre-processing bias mitigation method. If they're applied on the AI algorithm itself, they are referred to as to in-processing bias mitigation methods, and post-processing bias mitigation methods act on the output of the training model. And if you're interested in this area, you can read another recent survey we wrote about what are these bias mitigation methods, what has been proposed so far for machine learning classifiers. I'll give you just an intuition of how a bias mitigation method is expected to work. So you have a classification model, original classification model that has been trained on some data, and when applied to unseen data is expected to give an output. So the output of this model may fall in one of four regions. So this star is the original model. And if you see on the two axes, we have accuracy, because a model is still expected to perform with a certain accuracy in their prediction, and we have one dimension that measures the bias. So this original solution is there, and when we apply a bias mitigation method, we can have one of four possible solutions. We have a win-win region where we are able to optimize both the accuracy of the model and reduce its bias. we have a lose-lose region where we actually increasing the bias and also worsen the accuracy. And definitely you don't want to get in this region. And we have what is called a trade-off region, which is basically a region where models more often fail because the win-win scenario in reality is very hard to achieve. And when we apply bias mitigation methods, we always end up in reducing a bit of accuracy. So how much of this trade-off we can afford is the interesting part. And the remaining region describes the opposite case where they want the case where we improve accuracy and further worsen bias. So up to 2021, there was no baseline to automatically evaluate and compare these bias mitigation methods, and we came up with a solution to assess how good are these bias mitigation methods, because we feel in the trade-off area, we need a measure to understand, given to bias mitigation approaches, which one is more effective. So if we zoom in the trade-off area, we can have, every time we apply a bias mitigation method, we can end up with a different circle, right? So different methods will give us different accuracy trade-off. How do we assess which of these is better? So you see here, the star represents our original model, and we can make variants basically with different accuracy bias trade-off. And the baseline we introduced, which is called FARIA, is basically constructed by connecting the fairness accuracy points of the original model and the series of naive mitigation methods that will be by mutating the original model, basically. So any novel proposed bias mitigation method is effective if exhibits a better trade-off than this line. So if it's above the blue line. So we can use this approach to measure how good of a given trade-off is produced by a bias mitigation method. And we have taken existing bias mitigation method, 12 of them, published in very good venue, and we use them to solve 3 real-world decision tasks. For example, decide if people should get a loan or not, and use different metrics. And we found out that 49% of these approaches reduce the accuracy a lot. So they end up in the lose-lose case, basically. And this shows the importance of having a baseline like this. And this is made open source online. Later on, we extended the study with 17 bias mitigation methods and 8 real-world decision tasks. And we find that bias mitigation method significantly decrease the performance in 53 of the study scenario, and the improved fairness in 46 of all the scenarios. And some of these bias mitigation methods even lead to decrease in both fairness and ML performance in 25% of the scenarios. So they were in that purple region. So those methods should really not be used in practice, not even been published, according to what we have found, basically. So it's really, really important when we propose a new bias mitigation method to make sure they're actually effective. So to give you a more bigger picture, software fairness requires more than a fair prediction model, because this model needs to be fair while maintaining a satisfactory accuracy. So as we've seen in our study, 25% of the model were worsening, 50% of the model were worsening the accuracy, 25 were even worsening both. So it has been proved that design systems to improve for fairness very, very often decrease accuracy. And this phenomenon is known as the fairness accuracy trade-off. And moreover, the model needs to be used by practitioners in real-world environments where the notion of fairness may differ depending on the application domain. What is fair? So there's a gap between who build the models and who use the models. So the prediction model and the decision maker are not the same person, and we need a way to reduce this gap. And my take here is that search-based software engineering can help to strike an optimal fairness accuracy trade-off, exactly as we said, and we seen for the energy consumption, where we were able to strike the optimal trade-off between energy consumption and accuracy. We can do the same for fairness, and here there are two papers that shows that this is possible. We had applied multi-object search to create accurate and fair word embeddings, and some colleagues have worked on how to create accurate and fair machine learning classifiers, basically. So if you're interested, you can read more on this topic in this paper. And I also believe that SPSC can aid to bridge the gap between the two, so prediction model and the decision maker. In fact, in order to alleviate this problem, we can use an approach called multi-objective ensemble generation that leverage the power of multi-objective algorithms to automatically search for optimal ensemble according to both accuracy and fairness. And the decision maker can choose their own preferred fitness function. This is some work that is undergoing, so I don't have detailed results to show, but the preliminary insight we've got is that this is very, very promising. And last but not least, SPC can also help engineers tackle a more challenging notion of fairness, which is called intersectional fairness, which encompasses multiple sensitive attributes simultaneously. So far, a lot of bias mitigation approaches have tackled the majority of them, like there are very few, the majority of them tackle one attribute at a time, and it's much, much harder to optimize for all of these at the same time. And this is an open challenge. We haven't worked on this yet, and I think the community could investigate the use of search-based approaches to tackle this problem. So that's it so far. I've discussed the way in which search-based approaches can help developers achieve the automated optimization of non-functional properties for AI software system, such as energy consumption and fairness. And before concluding, I would like to thank the members of my group at UCL and the many international colleagues who I've had the pleasure to collaborate with on this journey. Thank you very much for your attention. I'd be very happy to take any questions from the audience.
Yeah, I had one more question. So when you were talking about software fairness, if I take the example of the recent data manipulation that happened in Harvard, so the case that happened. So how do we tackle the data itself being manipulated by the people who procure it? So, and because do we go case by case or do we use software solutions? So I had a question regarding that.
Yeah, the solution I mentioned, that the biasing mitigation methods, especially the pre-processing one, they're able to identify unfairness in the data. So they can remove this unfairness from the data directly. Data is historically biased, right? Because they inherit the bias that as a society we we have, or some of them may be maliciously altered. So before applying these models, we can build on top of them some testing and repair, automated repair by using bias mitigation methods. So this can be achieved via software, automated solution.
Okay, thank you so much.
You're welcome. Thanks for the question.
Thank you, ma'am. On behalf of ACM VIT, I extend heartfelt gratitude to Dr. Federica Sarro for sharing her invaluable insights on search-based software engineering. Dr. Sarro, a distinguished professor of software engineering at University College London and a leading expert in her field, holds an impressive H index of 40, reflecting her significant contribution and impactful research in software engineering. Her presentation today has not only deepened our understanding of search-based software engineering, but has also equipped us with practical insights and knowledge that we can apply in our own work. I am sure that the participants are leaving this session with a richer perspective on the topic and a better grasp of its real-world applications. I would also like to take a moment to recognize Dr. Aswani Kumar Cherukuri, our esteemed faculty coordinator of ACM VIT. His unwavering support and motivation inspire us to constantly advance and strive for excellence in every initiative we undertake. Finally, I would like to thank SCORE, School of Computer Science, Engineering and Information Systems, for making this speaker session possible, and all the participants for their active engagement and enthusiasm, which drives us to continue delivering these enriching sessions. Once again, thank you, Dr. Sarro, for taking the time to share your expertise with us. We truly appreciate your commitment to advancing our knowledge. Thank you.
Thank you to you. I'd like to thank you again for this invite, and thank you the ACM Distinguished Speakers Program to support it as well. And if you're interested in this research, you're very welcome to get in touch, and I'm available for mentoring, collaborating, hosting scholars from everywhere in the world, really. So thank you, and good luck with your program.
Thank you.